Hello, everybody. My name is Michael Beetz, and I'm coming from the Institute of Artificial Intelligence at the University of Bremen. And I want to talk to you about how to plan and how to learn very complex manipulation tasks for human scale tasks and in very natural environments. So the kinds of tasks that I'm thinking about is how can we generate the motion that a robot has to execute in order to perform a task like setting the table. And in our group, we are not tackling that problem as a problem learning the mapping from pixels to forces, but we'd rather like to have programs that are executing that, and the job of the robot should be to self-program kind of general plan schemata and to apply general knowledge in order to do that self-programming. So let me give you an example. So a typical task is a task like pour the water out, which in our case might be formalized as a symbolic expression, perform an action of type pouring, where the theme of pouring is some substance of type water. So, in our view of the problem, a robot can only generate robust and flexible behaviors to accomplish that task if it's capable of inferring the motion parameters that are needed in order to satisfy this task. And that means that the robot has to infer that in this case it has to grasp the pot by the handles. It has to hold the pot horizontally in order to avoid spilling. It has to tilt the pot around the axis between the handles, and it has to hold the lid while pouring. Only if you can make these kinds of inference, if you kind of infer the information that is needed in there, you can hope that you can have robot control programs that would work in a general setting in open environments. So the way we are going about that is that we take the assumption that we can formalize actions in terms of planned schemata. So if we take an action like fetch and place, so we are formalizing a plan to fetch any object that we know to any destination that it has to be at. And the top level plan looks abstractly like that. In order to fetch and place an object, the robot has to be at the location where it believes the object to be, and at that location it has to perform the action of fetching the object. And then it has to perform at the destination of the object, the action of placing the object at that particular place. Of course, the reason that this program is so elegant and so compact is that we allow a lot of hand waving. We don't specify what the locations are, how the fetching and the placing is to be executed. So if you have these types of plans, you also need schemata for motion plans. And a motion plan schema would look like that. So if the robot is already at the position and it wants to pick up an object, this happens, or we can imagine that this happens in motion phases. So we have a motion phase: reach, lift, transport, and release. And if the robot executes reach motion, then it has to commit to what is a pre-grasp pose of the hand, what should be the final grasp pose of the hand, and what should be the grasp force. So these are the knowledge preconditions that you need to satisfy in order to be able to parameterize emotion. And the goal of the emotion is to have contact between the hand and the object. So at execution time, so if we call this plan with a particular fetch and place action, so we can basically take the expression perform an action of type fetch and place where the object acted on is an object of the type cup, and place it on a location on the kitchen table. So as we have seen, in order to execute that action, we need to infer the parameters of the motions. So, so the first thing we basically take the parameters of this action and instantiate them in the body of the plan. Then we extend the body with knowledge preconditions that we know that the motion plans actually need. And then, in a nutshell, what the robot has to do, it basically has to answer the body motion query. The question of how do I have to move my body in order to accomplish this task. So this means in that specific case that it has to query the prefetch pose, the arm with which it wants to pick up the object, the grasp type, the lift pose, and it basically has to select parameters so that the action of fetching the cup has to succeed, right? And the reason that this kind of inference is so complicated is that ensuring that an action will succeed requires a lot of knowledge about the physics of the environment, but also a lot of common sense knowledge, like what is the arrangement of objects on the table for a breakfast setting, right? And things like that. And this is not all that we need all these different types of knowledge. We also need components like anticipation, like imagination, like experience, right? So when we grasp the cup, we want to grasp the cup such that if we are placing the cup on the table, the motion from placing is still possible, right? And so the robot already has to decide how to pick up the cup, having in mind on how it wants to put down the object later. So the hypothesis that we have is that we can realize plan libraries with manipulation plans that are very general and very flexible, very robust, and that can generate very competent context-sensitive behavior for all kinds of situations by coupling a generalized plan, a plan that we have seen before, with a knowledge base with generalized pieces of knowledge. And generalized pieces of knowledge could be something like cups used for table sitting have to be clean and unused. People might have preferred cups. Clean cups are in the cupboard. Cups have to be grasped from the outside. We have to parameterize motions to avoid unwanted side effects. Spilling is an unwanted side effect of pouring. The pose to pick up a heavy pot, and so on. So the game that we are playing is that we want to have these general pieces of knowledge, and the reason we want these general knowledge pieces is that they actually apply to situations that the robot has never seen before, right? So by combining these knowledge pieces, we can apply the robot to tasks that are outside of its experience. Another very nice effect of using that kind of representation is that by looking at the knowledge pieces when they are formalized in a machine understandable way, the robot essentially understands why it performs a motion in a certain way and not in another one. So the question is, does it actually work, right? And we can see here an example. So this is the task of setting the table. You see here is the belief state of the robot. You see that there are often appearing distributions of places of the robots, like here. And this is basically the inference that the robot does. It has to go at that kind of location in order to perform the action, right? And you see that these plans are general enough to open containers, to pick up all kinds of objects out of the containers from different configurations and place them. So the inferences that are performed in order to accomplish these tasks are basically all motion parameters we have talked about are inferred explicitly through inference tasks, and it's also that the robot basically infers each of these parameters through an inference task. So whenever it makes a certain motion, it knows about all the reasons why it has chosen the motions, and it can also record the parameterization that make it successful or not. And you also see that if you do that kind of game, it's extremely important that plans are very robust. And by robust, we mean, first of all, that they detect when they fail and basically try again with other parameterizations. So here you see that the same fetch and place task is now used for different tasks. Now instead of setting the table, we perform a cleaning task. And so that means the placing is now throwing away an object. We perform here the fetch and place task with a robot with very different kinematic. And we here reconfigure the environment, and here we basically perform an assembly task with the same fetch and place plans. So this is kind of the generality you want to program your robots with. So the kind of technique that makes such generality possible is, first of all, knowledge representation, a technique that has been developed in artificial intelligence for a long, long time, right? And the idea is essentially that you can represent the world as a collection of logical formulas. And when you do that formalization, you can constrain the way the world behaves through logical formulas such that you can derive anything that is true if these things hold and so all the implicit knowledge. And you can also ensure that the knowledge bases you write kind of they allow you only to infer things that are true when your preconditions are true. So this is kind of very important, right? Because what that allows you is that you can write control programs that make inferences, and you can trust these inferences that they are correct, and you know that the inferences are kind of complete. So that means if there is a solution, you will find it. So kind of the game that is played in these symbolic languages, that you define a language in which you can formalize your knowledge. And the language is defined in a recursive way. So the primitive elements are the constants and the variables. You can combine them to terms, and the terms you can use in order to build predicate logic formulas, and you can make the formulas more and more complex. The important aspect for me, if we apply that idea to robotics, is the constants. So the symbolic names that we use to represent entities in the world. And in logic, in artificial intelligence, when we choose these representations, these constants, they are typically chosen to be very abstract entities. So we have one entity which is a left drawer, in which kind of the plates are. And we have a left shelf, we have a right drawer, and a right tabletop. And this is problematic, right? And because these constants, the primitive elements of our logical language, they are very abstract, and they are it's difficult to ground them in the perception system of the robot control system. And if you have something like the pot or the right shelf, it's very difficult to take that abstract specification and generate the right motion from it. So these atomic entities, they also occur the same problems when we represent actions and change, right? Because now if we have these abstract representation of states, we basically want to represent the actions. So the representation that symbolic representations give you, they are essentially that you can go from one state, like here, where the lid of the pot is in the drawer, to another state where the lid is on the right-hand side of the tabletop in one atomic action, right? And that is pick up the lid and place it on the right tabletop. So if you think about it, right, and also if you think about the great success of deep learning methods, right? So what's happening in deep learning is that you take a very old idea of learning in neural networks and you combine it with high compute power and with incredibly big amounts of training data. And what I believe is you can basically apply the same idea to symbolic knowledge representation. So if you look at modern virtual reality environments that are used to render the world and also to simulate actions, so one of the things that we can do is, instead of kind of having very sparse representation of the environment, we can actually go and say, we take the data structure that represents these scenes in virtual reality environments, the scene graphs, and we basically take each relevant data structure that is relevant for the robot executing actions and turn them automatically into constants in our symbolic language, right? And if you do that kind of thing, that means this picture with all its little components, with the button of the TV, with the loudspeaker, and even components of the loudspeaker, it's a gigantic logical formula that is representing. And that's kind of the basic idea we are going about. And this concept is called a digital twin knowledge representation. So you basically represent your environment as a pair of a symbolic knowledge base and an artificial world. And in the artificial world, you have mechanisms for rendering the world and for simulating it. So what we want to achieve is that the artificial world that is part of our knowledge base is so close to the real world that if we are executing a control program in the artificial world and in the real world, by looking at the log files that the robot control program generates, we couldn't distinguish whether the control program was actually executed in the artificial world and the real world. If we are managing to do that, we can play a kind of a very cool trick, and that is we can make the robot control program believe that it's executing its actions in the artificial world, but in reality, it's executing it in the real world. And the fact that both worlds are matching so closely actually achieves that the robot control program is working properly in the real world. Of course, both worlds will never be the same, and we have to pay for that by making the robot control program very robust. It has to basically detect all events and failure detection, and it has to have mechanisms to continue from all detected failures. So, but one of the key questions is, can we actually build knowledge bases that are so detailed in order to do that? And of course, for environments like kitchens, apartments, that's still kind of ahead of us, and there are huge problems for doing that. But there are some environments where we already can do that kind of thing, and that is environments where we can do that are environments like retail stores. So retail stores are very nice because they are nicely structured. The products are placed so that they are visually distinctive and that there are little occlusions. So there's a lot of structure that makes the problem easier. So what you see here is that the robot is building a model of the real world in the artificial world of its knowledge base, right? So it starts by detecting the individual shelves. Now it's going along the shelves, detecting the separators between the different products. It's detecting the barcodes for the products, and then it basically detects the objects in the shelves in order to fill them. And this model of the environment, that is now a symbolic knowledge base, right? So you can go and ask questions like, show me a product with a a certain name, and we want to show that facing, and we basically get the information where that product is placed in the shelf. Or we could ask questions like, where in the shelf systems are the empty spaces, right? And we get all the places for products where products are missing. Or we can ask, if we combine it with background knowledge, we can ask questions like, where do items stand in the shelf that are dangerous for kids but within the reach of kids? So the cool thing about that is that we build an environment representation where we can ask questions about it. But this is not all, right? So because this representation is also an artificial world, we can take the knowledge base and transform it into a virtual environment. And now in the virtual environment, we can perform actions. We can do things like going shopping in the environment. And because it's a knowledge base, because we have a simulator, the system is automatically able to recognize the action. So we can see the trajectories with which the human has picked up the different objects in the shelf system, in the shelves, and put it into the basket. And we can use this data as training data for learning robot motions to put fetch and place tasks in the environment. So here we basically have an environment map that is built by a robot, and now the robot is supposed to fill an empty spacing, and it's generating the motions for that abstract task out of the knowledge base that it has constructed autonomously. And here we see how the system actually scales towards real-world domains, and how it's building maps of real shopping environments. So, as we have seen, kind of having such a detailed and almost continuous representation of the world, and being able to record that data during execution time, that means if we have log files that we construct from executing robot plans, those log files, they are so detailed that using queries to a symbolic knowledge base, we can generate videos like that. We can display the images that the robot has taken while executing the actions. And we see that this is kind of a very comprehensive representation of what is happening. So the data structures we record when the robots execute the actions, they are sequences of images. They are the poses of the robot control system. But on top of that, we completely record the internal operation of interpreting the plan, the tasks and the subtasks that are called, and most importantly, the events that take place when the interpretation of the plan is actually generating physical motions or reacting to perceptions that the system has taken. So, and each of those events, like the perception events, they are recorded as facts in our symbolic language. So here we have a perception task where we were looking for an object that satisfies a certain description. This was a result of the perception task, and it was computed based on a certain image, and the object was detected in a certain region in the image. So that's kind of the level of the symbolic representation that you can expect from such a log file. And now that we have these log files that are constructed automatically when robots execute the task, we can ask questions, right? So we can ask the question of, give me an action of the type pickup, where the robot has picked up an object of a certain weight, and the weight was more than 2 kilograms. And for that task, we want to know when that task started. And we want to know what was the pose of the robot at the starting time instant. So if we have that, right, and we have huge collections of episodic memories, then we can automatically construct learning problems out of that, right? So we can basically ask for the set of poses in which the robot tried to pick up a heavy pot and where the task outcome is success. And we are collecting these episodes, the poses that the robot has taken in these episodes in one variable that are the poses for successful picking up action. And we can do the same for failed pickup actions. So now we are basically using that for learning concepts like here, for example, learning the concept of the places from which the robot can pick up objects successfully. So here you see discretization of the places of objects on the table. The red points here are the poses that the robot took from which the pickup failed, and the green ones are the ones from successful pickup actions. And now we can basically take the learning actions, we can back project the places and learn a representation of the places from which to pick up at. At execution time, we get perception of the objects we want to pick up, but they are inaccurate. So kind of the position estimate jumps. And for each perceived estimated position, we back project the place from which to pick it up. And we essentially get a distribution that gives the likelihood of the pickup action being successful when if the robot stands and the respective. And here you can basically see that it makes sense. So if you change the pose, you see how the place is actually changing. And here you kind of see how that is executed in the real world. So obviously, the idea is that you basically take all the decisions that the robot has to make in order to generate motions in your original plan schema, right? And you basically want to learn all these motion parameterizations based on the episodic memories that you have collected, right? So to conclude, so I have proposed an approach to learning the mastery of everyday manipulation tasks that leverages that the programs executing the actions are not end-to-end black boxes, but rather that we have explicit representations of the programs and the robot does some form of self-programming on these plan schemata. The second ingredient for success is that we basically learn and apply generalized symbolic knowledge out of that, but the episodic memories also allow us to ground the symbolic representations in the continuous parameter space. We have demonstrated that this approach can produce generalized plans that generates flexible, robust, and context-sensitive behavior, and that it enables the realization of robotic agents that know what they are doing. The essential cognitive capabilities we need in order to realize these cognitive capabilities are a novel form of symbolic representations, which are essentially implemented on virtual reality environment representation scene graphs and the symbolic and sub-symbolic episodic memory. Thanks a lot for your attention.